a couple housekeeping things. First, I've been with Panduit and PTD for about 2 years now, so I'm starting to really get into these standards and have my own interpretations of them. And but I will say too that the standards and sections of these standards that we're going to dig into here are my interpretation of the standards and how I read them, how I would apply them, and not necessarily the, I'm not an official of OSHA, NFPA, or UL if we make it that far. But just keep that in mind, right? It's my interpretation, and I've got a few comments and questions to bring up along the way based on my perceptions of what they are and what they lack. And the next thing, Jenny mentioned it briefly, but we'll have some Q&A at the end. Hopefully we can get through some of this quickly. So please just post questions up in the chat, or I guess submit them via the platform, and we'll pick the questions that we have time for at the end. And but it really depends on how we get through this. So with that, let's dig in. So what we're going to cover today are relevant standards for AVTs and Verisafe, and I guess specifically a couple sections within them that seem to come up quite a bit in discussions that I have with customers. This is not a what's changed year over year between 70E or OSHA standards or 70B. This is, as the standard is, the most updated version of the standard. So the ones that we're going to cover are OSHA 29 CFR 1910, specifically Subparts S and Subpart J. Industry standards, so I guess the regulation, OSHA 29 CFR 1910 is a regulation, really the what needs to happen, that's regulation. And then the industry standards, more so the how to accomplish the what, being NFPA 70E and 70B, those are more process standards. And then finally, if we make it that far, this one's a little less impactful to the typical user, but the how, the product standards, the UL 1436, which is the standard that AVTs are I guess I'll say governed by. So getting into OSHA 29 CFR, what is it? Starting from the very beginning, right? OSHA, everybody should know this, but it's Occupational Health and Safety Administration. 29 CFR is the Title 29 Code of Federal Regulations. These are regulations that you must follow. If you do not, OSHA will come and find you and fine you, F-I-N-E, as well as fined, F-I-N-D. So Part 1910 is Occupational Safety and Health Standards. There's a whole bunch of different parts and so on. And the two subparts that we're going to look at are J and S. So J is the general environmental controls, and subpart S is the electrical section. So there's also a bunch of different subparts just for general comment on OSHA 29 CFR, right? There's subpart D, which is walking and working surfaces. E is exit routes and emergency planning, right? So OSHA really tries to define requirements for all these different categories, really around employee safety. How do they make sure everything's safe? I was actually watching a Netflix documentary the other day on killer whales, and OSHA was even involved in killer whales and how the trainers were no longer able to swim with the killer whales, which is an interesting comment. But then specifically in section, or in subpart J, section 147, and then in subpart S, 333. There's a range for each one of those. They're all broken up, but those are the two areas that we're going to focus on here today. So with that, subpart J, the first part of 1910, the energy control procedure. So this is the first time that they start mentioning that there needs to be a control procedure of potential hazardous energy. Now keep in mind this hazardous energy in this section, which is just a general environment of workplaces, is not specific to electrical. It is thermal, and then different mechanical energies as well. So kinetic, like flywheels or fans, and then different potentials as well, like springs or a lifted mast that might be up for some reason, some machinery like a crane or what have you. So essentially, you need procedures shall be developed to control the hazardous energy. So that's the first semblance of it. And again, remember, it's not just electrical. It's all those other mechanical ones, and subpart J is not specific to electrical energy. That is the subpart S. So next portion of subpart J is there's similarities between this as well as in subpart S with the electrical control. But in subpart S, you have to apply the control, right? What are you going to do? So they define a bit of a process and that goes from 1910 147 D1 through D6, but it goes things like preparation for shutdown, then it goes into machine shutdown equipment for 2, and then 3 is machine equipment isolation, right? Then lockout, tag out, and then release the stored energy. And the final one is verify that you've isolated, a verification of isolation, right? So the authorized employee shall verify that isolation and de-energization of the machine or equipment have been accomplished, right? So they're not saying how to do it, they're just saying what needs to happen. And again, this is the regulation. You have to do this. That's why it says shall. That's a very important word in the standard speak. It's not a you should or you will. It's a shall, which is a requirement. So you shall verify that it's de-energized prior to being worked on. So now we get into Subpart S. So those are the couple, very specific sections of Subpart J that kind of set the stage for verifying de-energized equipment, and now we're going to get into specifically the electrical steps, which is where Verisafe and AVTs come in. So Subpart S, again, it's the electrical section, obviously focuses on the electrical portions of it, but de-energized parts, right? So this is one of the first sections that matters. Live parts to which an employee may be exposed shall be de-energized before the employee works on or near them, right? That's why you have to de-energize a cabinet before you enter it. In OSHA, it says that, or I guess CF 29 CFR 1910, it says that less than 50 volts to ground do not need to be de-energized. They're not hazardous. You'll see some consistency with that in 70E as well as we get to that part. But with systems above 50 volts, you must or you shall de-energize the equipment before anybody gets works on them or gets near them. So that is 1910 333A1, de-energized parts. Getting to the next portion, 333B24, verification, right? The requirements of this paragraph shall be met before any circuits or equipment can be considered and worked on as de-energized. So as this works down, how standard is right is B24B is just part of that verification of de-energized conditions. So this gives them a little bit more criteria of what needs to happen to be considered de-energized. So qualified person, right? A qualified person shall use test equipment to verify that the circuit elements and equipment parts are de-energized, right? You have to use equipment, and a qualified person must be doing this, and they must use that equipment to verify that it's de-energized. They shall also determine if any energized condition exists, backfeeds and induced voltages and so on. So you've got to make sure that it's not just your disconnects opening and it's de-energized. You've got to also make sure that there's not going to be another source coming in to create a hazardous condition. And the other interesting thing is that this is another thing of what needs to be done, not necessarily how, but this is very close to how. This is about as close as OSHA will get to how, but the section there in the yellow is for systems over 600 volts, the test equipment that's used to verify absence of voltage, to verify the de-energized state, must go through that live dead live test, right? That immediate test immediately before and immediately after you do that de-energized, that absence of voltage test. So it's very specific, right? Over 600 volts, you've got to do that. As you'll see in 70E later, there's a different level for that. That's 50 volts, but we'll go into that as well later. But again, the difference between regulation and more of like a law regulation type versus industry standard and best practice. But above 600 volts, you have to do this. Great, what does it mean for me, right? So just try to summarize all that text that we went through in the last few slides. First, you've got to develop procedures and document and use this control, use those procedures to control the exposure to hazardous energy, right? That's in the general conditions, the general environment. You've got to do that. You need to keep your employees safe and so on, and you got to document and train and so on. Next part of that is you've got to verify that it's isolated, verify that it's de-energized, verify absence of voltage of that equipment. Absence of voltage is the electrical part, but it's more than just electrical. You got to isolate and verify that it's isolated from a hazard with mechanical and thermal and other energies as well that could be hazardous. And then getting into the last two are more from Subpart S, the electrical section. Live parts shall be de-energized before work is performed on or near. and it really is just talking about voltages over 50. Under 50 volts need not be de-energized. And then I guess the last part to take away from OSHA 29 CFR 1910 is that you have to meet certain requirements before you can consider this equipment to be de-energized electrically. And that is, a qualified person has to use test equipment to do it. You can't just visually inspect it or listen to a hum or no hum, right? You've got to use test equipment to verify that the voltage is absent or it's de-energized. The test shall determine if there's other energized conditions. Induced voltage and backfeed was specifically brought up, but right, anytime there's a hazardous condition that is present beyond just the main feed, got to verify that as well. And then the last thing I mentioned as well is that specifically on 600 volts or more, the test equipment should go through that live dead live, that operation verification step to make sure it's functioning properly, right? Because the whole thing with the life safety process is you want to make sure that these things work properly. You don't want to find out the hard way, right? So that's OSHA. That is, there's some there, but that's OSHA. So again, OSHA is the regulation. That is the stuff that is required by OSHA, and they will find you and fine you if you're not adhering to that standard. So it's an important one to make sure you know. So 70E, what is it? So 70E is more of a best practice industry standard. It's not regulation, but it is supported by OSHA. And many times OSHA will reference 70E. 70E was actually developed at the request of OSHA because they recognized the lacking of the how, right? Is you need more clarity and more standardization and give employers a reference of how to do this. So that they aren't all developing their own standards and have a lot of inconsistency across the industry. So it was developed for a reason. It's not just developed on the side and just OSHA doesn't care about it. They reference quite a few NFPA standards in their workings and letters and interpretations and so on. So the two specific sections, or at least parts of the sections that we're going to cover, are 110 and 120. So 110 is the general requirements for electrical safety related work practices, as they say up there. And 120 is how to establish an electrically safe work condition. So again, getting very much into the how, not just the what. So 70E, the first part in 110 is .6D, visual inspection and repair. So first, test instruments and equipment and all associated test leads, cables, power cords, probes, all the wear items really shall be visually inspected for external defects and damage before each use. This comes up a fair amount, and I'll just say that AVTs and other technologies beyond test instruments. Test instruments have been there for a long time, and that's really what a lot of these standards were written around, not AVTs being permanently mounted. So this one, I don't believe is intended for permanently mounted devices. It's more intended for portable test instruments, again, which have wear items. And as you're using these wear items or moving them around and they're getting abrasions and so on, they could eventually wear to the point where they are causing a hazard themselves. But with permanently mounted devices, they are in the cabinet, they're permanently terminated, and they don't have the same wear and therefore don't have the same needs for visual inspection and repair like a test instrument would. So that is one thing that while AVTs are in 70E now, and I'll cover that in a little bit, but this is one of the sections that I believe could use some refresh on the verbiage and what it's talking about. So that's more to come in my efforts working with 70 in the committees there. But for now, this is my interpretation, right? Is this is not intended for permanently installed devices like AVTs. So the next thing in 110.6 is 110.6E, operation verification. This is another one that I believe probably could use a little bit more alignment to the new technology out there of AVTs. So This is written very much around test instruments right now, but essentially you want to make sure that test instruments, your portable meter, are functioning before and after you use it, right? It's a life safety process, so making sure it works and you know the result it's giving you is accurate is important. So you do, per NFPA 70E at least, you do need to do this on voltages over 50 volts. As you saw in OSHA, it's over 600 volts, but NFPA brings it down to 50. So pretty much anytime you're performing an absence of voltage test, you should, on 50 volts or over, you should be going through that live dead live test on a known voltage source before and after your absence of voltage test is performed. But like I said, the text here is focused on test instruments and not just test instruments and equipment. And this is something that I feel, again, if you're using any equipment in between your voltage source and where you are measuring, you're going to want to make sure it's working right? You're going to want to make sure it's still functioning properly, it's still terminated properly, right? AVTs go through and validate that. That's part of the standard if we make it to the UL part of it. But yeah, you want to make sure your equipment's working right. Or else, you know, it could fail, just like a disconnect could remain closed. So it's an important thing to make sure. Getting into section 120.2a, the lockout tagout program. So essentially 70E is partnering with OSHA, right? Is you need to have a program, just like OSHA says you have to have a program that's documented and trained, and you have to roll it out to your employees. 70E also says the same thing, but they just call it a lockout tagout program. But it's a general, let's just say essentially, the lockout tagout program has to be, and I'm looking at those 3 bullets down at the bottom there, it's got to be applicable to the experience and training of the workers and conditions of the workplace, right? So you do need to tailor it to your environment and your needs specifically. Have to meet requirements 2 through 6 in 120. I'm not going to go through all those steps, but you can actually reference that pretty easily on NFPA's website. They have a pretty great sharing platform where you can reference any of their standards for free online. If you want to, of course, print them out or get a hard copy, you know, they'll sell them. But you can reference any of this content online for free, which is a good thing to mention. But the lockout tagout program, again, needs to be applicable to the experience and training of the workers and conditions in the workplace. So again, tailored to your needs, needs to meet those requirements that are defined in the standards. And then it has to apply to fixed, permanently installed, temporary installed equipment and portable equipment. So pretty much any electrical equipment that you've got that causes a hazard. So 123B, specifically some principles of lockout tagout procedures. So part of your lockout tagout procedure, which again is in that 120.2 through 120.6 covered in the previous point. 120.3 is one of those. But the point that I want to call out is it shall meet the requirements of applicable codes, standards, and regulations, right? So you've got to meet those requirements of OSHA. So anything that goes back and is in OSHA, you've got to make sure you're covering as well. So we covered a few of those points, but by no means did I cover every single point that you would want to recognize in OSHA. And again, OSHA standards are all you know, available online for public consumption as well. So none of that stuff is gated behind anything, any cost barriers or anything. All publicly available. Now getting into the area that most people think of when they think of absence of voltage testing in AVTs is 120.6, right? This is really where that bread and butter, that meat and potatoes, so to speak, or what is it from lamb and tuna fish, I guess they say that. What movie was that? I forget anymore. But anyway, 120.6, establishing and verifying electrically safe work condition. This is the process that you've got to go through, and it does align pretty close to what OSHA says in the steps that I covered a few slides ago. But I highlighted the kind of the main paraphrasing of each step, right? You've got to determine all possible sources of electrical supply to the specific equipment, right? So if you've got multiple feeds, you want to know all of them. You have to open the disconnecting devices for each of those sources, right? Again, makes sense. Step 3 is you got to just, if you can, visually verify that the disconnects blades opened. You should look and see if they've opened, because sometimes they do stick, and that's one of the failure points of this, and that's why we have absence of voltage testing, is sometimes those disconnects do stick closed. Something fails in them, they're mechanical devices. So if you can visually inspect it, great, visually inspect it. Release any stored energy, right? That could be capacitors, it could be a non-electrical energy in step 5, right? But release any stored energy in step 4. Step 5 is block or relieve stored non-electrical energy, right? Again, if it's hot, you got to let it cool off. It's spinning, you got to let it stop or stop it. If it's some sort of capacitance, you've got to either let it bleed down or somehow safely get it bled down. Step 6 is apply lockout and tagout devices. And then step 7 on the next slide. This is the one that is probably the most known in 120.6, right? This is the use an adequately rated portable test instrument to test phase conductors or circuit part at each point of work, and then test each phase conductors, both phase to phase and phase to ground, and then determine that the test instrument is operating satisfactory. So this is kind of like a duplication to 110.6E, which is the operation verification step, but just to double down on that, you've got to make sure that the test instrument is operating satisfactorily on a known voltage source before and after, right? So now this step 7, that's been there for I'll say decades, but a long time, right? I don't know exactly. I go back to look at previous standards, but been there a long time. That's been the primary method for decades. Exception number 1 to 7. This is where AVTs come in. This is an exception to this step number 7. So essentially an alternate method that you can accomplish step 7 is with an absence of voltage tester. So a permanent mounted absence of voltage tester can be used for this. And the sections I've got highlighted there, you'll see that it tests conductors and circuit parts at point of work, very much the same way as the first highlighted section in the the original step 7. Bullet point number 3 is to test each phase conductor, both phase to phase to phase ground. Again, the exact same way you would have to do it with the portable meter. And then finally, you've got to make sure that the device itself is working on a known voltage source both before and after the test. So that's not only the device itself needs to be confirmed that it's working, it also needs to make sure that it's still connected and terminated properly and measuring voltage properly, which is something that you can't quite do with a portable meter, right? You might get a 0 voltage reading, but you might not even be making contact with the conductor either. So AVTs do that and more, and the internal check that it does is very much just like if you were to, when you turn on your computer and it goes through and does all the diagnostics of the motherboard's not having any failures, the hard drive spinning and the RAM's there, it goes through whatever checks. I'm not that familiar with that process of a computer starting up to the specifics, but I know that it checks those certain points, and if something isn't right, it goes, prompts you for safe mode, or you get a blue screen of death, or you get some sort of failure mode that you're like, okay, something didn't check out, something's wrong. Verisafe and AVTs do that exact same type of process where it makes sure it's inside all the circuitry, the solder points, all the resistors, all of the things that it's expecting to receive back as a thumbs up, so to speak, that everything's working right. It's checking itself, like I said, very much like a computer does, and you know if it's functioning properly or not. So great, 70E, what does that mean? What does it mean for me? So summarizing it, right? When using a portable device, all leads, probes, power cords, and et cetera must be inspected for wear before each use. That's section 110.6D. Again, that's specifically from my interpretation. It is portable test instruments, portable devices, things that have more likelihood of wear on the cords, whether it be power cords, probes, leads, whatever. They are moving around, rubbing on things, going over edges of enclosures, right? If they're not painted, there's burrs potentially. So areas where you would expect wear, you just want to check it. So systems operating over 50 volts shall have their test equipment verified for operation on a known voltage source both immediately before and immediately after the test was performed. Again, this is the part that I mentioned that in OSHA, they say the same thing, except the threshold is 600 volts. NFPA 70E gets a little bit more precise and says, 50 volts. Anything that's over that hazardous, that 50 volt threshold, where hazards can be received, that's when you should be making sure that your equipment is performing properly. And then last, I'm not going to go into the 120.6, but employers shall have a lockout tagout program for all equipment that meets 120.2 through 120.6, and we just covered 120.6. But to sum it up, you've got to have a lockout tagout program, and it needs to accomplish those specific steps, and it needs to meet all applicable code standards and regulations. I guess that's kind of obvious, but if it doesn't meet those, why are you doing them? And then that's specifically from 120.2a and 120.3b. And then finally, the last standard that this is kind of not new. The 70B itself has been out for a while, but it just recently changed from a recommended practice to a standard. And what does that mean? So I guess first let me back up. 70B is more of electrical equipment maintenance, and the whole point of the standard is that I'll just read it from here. So it elevates the status when it went from a recommended practice to a standard. It elevated its status to increase its recognition as a benchmark, right? So now it's more trusted. It's getting momentum, so to speak. And really, it's meant that if you don't have a maintenance program, you may need one. Right, having a robust lockout tagout process will help reduce the risk of and severity of incidents, if and ultimately when they occur, right? Because realistically, they are going to. Obviously, we want a zero case, but realistically, they will occur. So 70B encourages employees to consider their own environments and how that may influence their electrical equipment's maintenance needs. It's not defer to 70B if your equipment doesn't have a recommended maintenance from the manufacturer. It's more so, hey, if your equipment's old or new, it might need different maintenance requirements. If you're in a very dirty environment like mining or sewage treatment or that sort of thing, it might be have different requirements than if you're in a pharmaceutical or a clean room or a data center or so on. So I'm not saying one might require more or less. It's just it needs to be considered in different ways, and this standard is there to help guide and standardize on how that is accomplished and so on. So that's it for 70B. I wasn't going to go too far into it, but I do want to cover different testing technologies that are commonly thought of when voltage presence, absence of voltage is thought of. So first and foremost, portable test instruments. Like I mentioned, they came up a long time ago. They've been around quite a bit, and different pros for that. They're portable, they're inexpensive, they have many different uses, right? So their uses expand beyond just absence of voltage testing. There's tons of uses for them around facilities. Some of the challenges, right? There's different device ratings and versus the equipment that you're using them on, the operation of them. There's different settings that you just have to make sure that you're using it properly and you've got it set up properly. When you're going through absence of voltage testing, you do need to use PPE, which can be cumbersome and costly. You've got to make sure you're making proper contact because it is, a person's hands and that ergonomics there, trying to make contact, and sometimes you're having to work through tight spaces, and there's just different things that they're just challenges, nuisances that come up that may hinder the effectiveness of their use. Second, permanently mounted indicators. They are great. They're passive devices, right? But they'll illuminate with presence of voltage. So they're great for showing presence of voltage, right? If there's voltage present, they should be illuminating and letting you know that voltage is there. So the pro there is it's a quick visual for voltage presence, right? You can see it. It's great. The challenge is there, right? It's a hazardous voltage typically is brought to the panel door. So you do need to bring that forward. And then because it's just a passive device, there's no way for it to validate connectivity. So no way for it to validate that those connections, those leads are still terminated properly. Sometimes they are solved in high vibration environments or environments that might cause those terminations to come loose over time. There's no way for that device to verify that that is not the case and it's still connected properly. And secondly, there's no way to validate that the internal function of the device is still okay. Because again, they're mechanical electrical components, they heat up, they cool down. That will cause wear on the solder points and the PCB boards inside and the electrical components inside, and eventually a failure could occur. And that's one of the reasons, or these are kind of the reasons why permanently mounted indicators are generally not considered a safe way to verify absence of voltage, because it's a passive device and it can only verify that voltage is there, and there's no way for it to verify all these other failure modes have not occurred to give you without a reasonable doubt at all that there's voltage still there. So not quite the greatest for absence of voltage testing at all. So next, portably mounted test portals, right? Very much kind of in a similar vein to indicators, right? They're passive devices that should enable measurement of presence of voltage. So not only do they illuminate, but they allow you to measure that. So that really, in some ways, really to dumb the technology down, you're no longer seeing a visual illumination of an LED. You have a point where you can put a portable meter to measure that voltage that could illuminate an LED. Right, so the pros, you can obtain voltage measurements without opening the panel door, right? So if you do need to get voltage measurements or what have you that you could pull from those points, you can do so without opening the panel door. So from that sense, they're great because you don't have to go into the panel when you normally would, and that is a hazard you are avoiding. Some of the challenges, right, is typically, again, just like indicators, hazardous voltages brought to the panel door, right? So it's going across hinges and it's to the back of that panel door. So that is a risk that you're adding. And then again, very much like permanently mounted indicators, because they're a passive device, they have no way to validate that they are still connected, and there's no way to validate the internal function that nothing has failed inside the device. You again, going back to high vibration environments, many of the environments that these devices are installed in are not just very clean or very stable as far as like very no oscillations or vibrations, right? So there are failure points, and there are still mechanical electrical pieces in there, the resistors and solder points and PCB boards, all of which, if those fail, there's no way for you to verify that it is still functioning properly. And then finally, the last technology that's often brought up with this absence voltage testing, which is no shock, right? Absence of voltage testers, per the name. And this is the only device of these four that is an active device. And this active device is an automation of that absence voltage testing, essentially. So that's where a lot of the human error gets pulled out. You push that button, it's all pre-programmed to check itself, check all these different items, and to go through that process, right? So it automates that absence voltage testing process, takes out that complexity, takes out that time, takes out that hazard of having to get in there with a portable meter and a PPE, and it also verifies that it's connected properly and its internal components are functioning properly. So when you push that button, you do have confidence that it's going to give you a good confirmation when it is safe, right? You will only get that green light and that it is safe to enter if it is actually safe to enter. You will not get a fail when it goes green. So the challenge is permanently mounted. So comparing that to portable test instruments, right, it's not portable, right? So you do need one absence voltage tester per voltage source, which can be a cost hindrance relative to portable test instrument, right? Because you can use one portable test instrument for many different installations. But the big difference there is the risk that you're eliminating, and the complexity and the time that it takes to accomplish those tests. So there is a trade-off there. So looking at them a different way, right? So when you step back and look at those four, actually I should have put them in the right order, but in the same order as the last slide, but I didn't. So when you look at those from left to right, you've got the indicator, right? Again, it's on the panel door. You bring each sensor lead over to the device, and it's got illumination for whatever it's connected to. I've got a 3-phase system showing there, but if it's a DC or single-phase system, they have specific SKUs for that too. But the technology is the same, right? It's a single test connection to the conductor, and then to the panel door. Test instruments, you do have to open up the panel door and then enter in. You've got to put your PPE on to do that, right? Because before you have verified absence of voltage, you have to assume that there is still voltage present, which means you need to protect yourself based on the cal rating of that panel. And that comes with, I'm not going to get into that, but that comes with different criteria for what PPE you need to be wearing. A portable and test instrument, that's essentially what you do for measuring voltage presence. But again, because you cannot verify that that portal is still connected properly, or there isn't a failure point within that device, they're not that great, or not really accomplishing the absence of voltage test properly. That's my interpretation of it. But again, it's not to say that the portals don't have a purpose, they don't have a value, right? You can still get those voltage measurements with that panel door shut, and that does add value, but that does not accomplish absence of voltage testing. And then absence of voltage testers in Verisafe, right? You've got the redundant leads, you're able to verify that it's connected properly, it does all the checks, and it does all those checks that the test instrument would do with a human at the push of a button, because it's all programmed and predetermined in there. And with that, Jenny, that is all I had there. Have we had any questions come in that we should just jump into? Do we have time?
I think we have time. I think we have time for a couple of questions.
Okay.
So our first question is NFPA 70E required to be followed by federal and state?
Sorry, I was just drinking my water there. No, 70 is not a requirement to be followed by federal, state, and in a sense that it's not a regulation. It is widely recognized by industry and employers, though, and OSHA, that it is a guide to accomplish OSHA's regulations. So it's not really a requirement per federal or state regulations, but it is referenced by OSHA, and it is a good idea to maintain compliance with OSHA. So that's kind of the benefit of 70, is it helps employers meet their obligations under OSHA's 29 CFR 1910 specifically. So good question.
Okay. I think we have time for one more. Why is it important to ensure devices that are used for these processes are functioning? My multimeter hasn't ever failed beyond batteries, and it just doesn't turn on at all when that happens.
Okay, so because I'm understanding that question is the only time that this individual's multimeter has quote unquote failed is when the batteries have run out, and it's worked fine for him or her every other time. So yeah, that is definitely one of the failure modes, but fortunately that one is a failure mode that you can pick up on right at the very beginning of the test, right? You turn your dial there and it doesn't turn on, but it's not the only failure mode. So because you've got the dial there, you've got to make sure you're on the right settings, right? If you're on the current or your DC settings, when you're measuring AC, you're not going to get the right measurements, and so on. So, but yes, I agree. And theoretically, if everything worked as it should every single time, there would be no incidents. There would be no need to verify that you're making sure your devices are functioning properly. But realistically, that's not the case, right? That's why you also have the visual checks for disconnects, right? That's another device that more often than not, it functions just fine. You open that disconnect, it functions fine. You use your multimeter, more often than not, it's going to work just fine. But the key to keep in mind with absence of voltage testing is not that you're just trying to make sure that it's working when it's working, because it's working, but you want to make sure that when a device fails, when it's not working, when that disconnect doesn't open, when the voltmeter pops a fuse, right after your live test, that you know about it, right? Because when you know about something, you can act on it. If you don't know about something, you're not going to act on it because you don't know about it, and then you could enter that panel, and it could still be, hazardous voltage, hazardous energy could still be present. So it's more than just the battery. There are failure modes, and again, it comes down to, you want to make sure when things aren't functioning properly that you know about them, because again, it's a life safety process, and you want to make sure you get it right every single time.